In this lab, we will use Newton's second law to predict the motion of a falling object. Newton's second law is defined as force equals mass times acceleration. In this lab, the system is a pair of socks, and the surrounding is everything else that surrounds the ball of socks. The initial velocity is different from the final velocity, but the initial velocity is zero since it is drawn from rest. So, the net force is not zero, and one engine is in the surroundings is exerting an influence in the system. The force that is influencing the object is the weight force and can be also called gravitational force, and it is pushing the object downwards. It is defined as force equals mass times gravity. Then I analyzed my video on Tracker, and I decided the coordinated systems to be the positive x-axis to the right and the negative y-axis down, and I used my height, which is 1.63 meters, as a reference for the video. Then I selected different points of mass during the video to create a graph and to get different data values that will be used later. Then I created a Python model to predict this movement. I used the mass of the pair of socks here to define the ball mass, and the ball position is defined as the vector 0, 0, 0 because it starts at the origin, and the ball velocity is also equal to the vector 0, 0, 0 because it starts at rest. I defined t less than 0.7 because the final time of my video is 0.625 seconds. Here, I defined the net force as equal to the weight, and I put the formula here, and I used Newton's second law to define the ball velocity and the ball position. Then I ran the model, and it recorded the movement of the ball downwards. The object moves downwards both in the experiment and in the model. This confirms that the weight force exerted by the surroundings is influencing the system. Also, both graphs look similar. Then I compared both graphs using Google Spreadsheet. The blue dots define the experiment and the red line is the model. For a small time, the model does a good prediction, as you can see here. But for a bigger time, the model predicts the object to fall farther than observed in the movement. This suggests that is another force influencing the system, which is air resistance, that can also be called drag force. Air resistance, or drag force, goes in the opposite direction of the movement, as you can see in the picture. Since the object is moving downwards, the drag force goes upwards in the positive y direction. We can keep using the data obtained from the analysis with Tracker. I created a new Python model using the same data that I used before, the mass of the pair of socks, that the position starts at the origin and the velocity starts at rest. B, here, is determined based on the final position, negative 1.633 meters, and it depends on the object. The final time keeps being 0.625 seconds. The magnitude of the drag force is proportional to the square of the object's speed. So now the force is equal to the weight plus the drag force. Here, I'm still using Newton's second law. Then I decided to draw some arrows. The arrow scale is equal to the magnitude of the weight force times 2 meters divided by this magnitude of the weight force. Arrow 1 is the weight force, and arrow 2 is the drag force. By running the model, you can see that the yellow arrow is the weight force and the blue arrow is the drag force. When the object starts to fall, we see that the yellow arrow is going in the negative y direction, downwards, and not changing direction nor magnitude. The blue arrow is invisible at first, but then it shows pointing in the opposite to the direction of the motion, that is, upward to the y plus direction, and getting longer as time goes by. It depends on the ball speed. At first, the object is moving slowly, making the drag force negligible, but as the object speeds up, the magnitude of the drag force is more significant. Here you can see that the three graphs look alike. By comparing the three graphs, you can see that at the beginning the model does not predict. This part sets the initial conditions for the model, and at the end the model does not predict either. It is used to fit the drag force model. In between, the predictions are not perfect, but the second model underpredicts the motion. It seems that the first model does a better prediction. This suggests that the gravitational force was more influential than the drag force. Some possible source of error could have been the perspective distortion, that the column looks a little twisted, and determining the centers of mass, and errors in the data and calculations. All these things could have affected the results. So, what does it mean? The terminal velocity is the maximum velocity where the drag force equals the driving force. The first model does not take into account the drag force, it only takes into account the weight force. Thus, it does not predict a terminal velocity. The second model takes the drag force into account, but it does not reach a terminal velocity because the gravitational force is bigger than the drag force. What if? If the object was initially thrown downward, then the initial velocity is not zero. This suggests that the final velocity of an object with non-zero initial velocity will be greater than the one of the object thrown from rest. The terminal velocity in this case will be different from the case where the same object was initially dropped from rest because the drag force is more significant and the terminal velocity is reached faster as the speed is greater. Thank you.